Back to the second session. So Douglas, is it, right?
Yes.
Will present us the Calysto Scheme Project. So the floor is yours, sir.
All right, great, thank you. This is a long meandering story in real time. It took 20 years to get here, but I'm going to try to tell it in shorter time than 20 years. The project is called the Calysto Scheme Project, and it's actually not just this particular implementation of Scheme, but some of the stuff that came after and around it. I have a colleague, in fact, my colleague Jim Marshall is the brains behind the outfit, but he is stuck on a tarmac in Newark, New Jersey. So apparently there's some big storms yesterday, so he never made it out. He would be doing part of this talk, but I will be trying to fill in, and so be kind to me. I'm not a programming language expert at all, and Jim has his foot in programming languages, but neither one of us are actually programming languages researchers, and I'll tell you a little bit more about that. So I want to go back, if I may, 20 years, and there was a project that Jim and I were working on right after we got our freshly minted PhD certificates, licensed to go out and do stuff. And we had both been working in cognitive science and AI, machine learning. And we immediately thought, we really need to work with robots. And 20 years ago, we thought, couldn't imagine like large language models that we see today, ChatGPT. We thought in order to have any kind of intelligence, you had to have a body. So you need to study robots. So we started this project called Python Robotics. And if you Google Python Robotics, there's a lot of Python and a lot of robots. But 20 years ago, this was a new thing. And it was sort of clever. It was a client-server architecture in Python that allowed students to write simple little brains that could connect to any kind of robot. And it contained a lot of stuff connected to AI, but it was probably the first implementation of a neural network in Python. But we were focused on the robots. And that actually led to another project that we ended up getting a grant from Microsoft Research, and because we were known for this Python robotics. And we were taking some of the sophisticated ideas of doing real robotics, but making it be easy enough to use in an intro class. So when I taught college at Bryn Mawr College, the first day of class, we would pass out a robot to every single student. And a lot of students were, whoa, what is this? No one told me that this was a robotics class. But it was really intro to computer science with a robot. The one big problem was that it was Python only. And so we sort of thought, it's really not fair that just, you can only use these robots if you use Python. So we started another project about 15 years ago, and I'm only going to talk about this project briefly, but it was called Calico. And the idea is that we wrote these libraries for music, art, robots, and it could be used, these libraries could be used with a variety of different languages. And so we had this one interface, Calico, where you could write in Python, or you could write in a language like, this was something we created, a block-based language we called Jigsaw. And basically, if you implemented those 4 buttons at the top, new, print, save, and run, then that was a programming language in this system. And we really enjoyed this, and students seemed to enjoy it. It was, its own little IDE, so it lived in its own little world. But we had all these different languages. We had, back in the day, F#. I don't know if people are still working with F#. Ruby. And we weren't sure 20 years ago what was going to be the predominant language used in introductory computer science classes. Python was just becoming popular, and I was an advocate for Python, and I think it's a great language for teaching. But there were a lot of other ones, and this was iron Python. All the system was written in C#. But there was a big gap in the set of languages. You might guess what that is. Scheme. And we were like, how can we come up with a scheme language that would fit into this weird little architecture where we have these libraries written in C#. So at the time, this was about 2007, there wasn't anything available that we could grab and use. So we set out on this mission to build a scheme. Now, why would we do that? Well, we weren't programming language people. We were, cognitive scientists that were interested in robots, but we were both at small liberal arts colleges, so we wanted to create this system that used Scheme. We love Scheme. We're both from Indiana University. We both got our PhDs there, but not in programming languages. Jim took a few more classes than I did. So we felt compelled really to do what we could 20 years ago to get Scheme into the minds of students. So our goals then were, it had to be written in C#. We're going to abandon that goal here in a second. But at the time, there wasn't anything. There were a couple of projects. There was something called Iron Scheme, and there was another one called Iron Lisp. These Iron languages were C# based languages. And they weren't ready. They didn't fit our needs. But we knew that there was a pathway from a continuation passing style interpreter into languages like C or Python or C#. So we set on this trip, we were going to build it. And we had no idea how hard or how long it was going to take. And soon after on this pathway, we actually did get it working for C#, but then we transitioned to Python for a couple of reasons. So, and this might be old news to some of you, although not everybody has actually had a programming language class yet, even though I know that some of you are presenting on programming languages. So here's the basic process to that. First, you write an interpreter for Scheme in Scheme, and then you convert it to this continuation passing style. Are people familiar with CPS? Okay, not everybody, but I'll show you an example in just a second. But if you write your interpreter in Scheme and CPS, then you can go through these transformations that are correctness-preserving. Make sure you can still have bugs in your code, but if you do the transformation properly, then you can transform that into a data structures format. And then if you do that, you can convert that into a register machine format. And then, and those are pretty straightforward processes. There's a lot of complicated details, no doubt. And then the last bit is fairly simple. Convert the register machine. These are all in Scheme. So this is write a version of Scheme in Scheme, convert it to another version in Scheme, convert that into another version in Scheme, and then convert that to C# or Python. So I want to be really concrete about that, so I want to give you an example. So I'm going to use this little definition of sum. It's a little recursive function, but imagine that this is actually an interpreter. So this is a Scheme interpreter. So sum is going to stand in the place for an entire interpreter. So you write it, and it works, great. But what we want to do is, in the first step, is we convert that to a continuation passing style form. And I'm not going to go through the entire details here, but wherever you have computation to do, you write a little function that contains that computation. And so in all of these examples, I'm going to have a little starter program, and then it's going to call into this continuation passing style version. So this is sort of a little header on this to get started this process. And so then K stands for the continuation, and in these places you apply the continuation, and then this is a continuation here, these little functions. So this is pretty mechanical. It's hard, to get all of the, and if you have a programming languages course in this style, you'll oftentimes, one of the assignments will be, write this function in continuation passing. Has anybody had to do that? Okay. Some old schoolers and not yet. Okay, this is coming. So that's the first step, and you learn that perhaps in a programming language class. What you don't typically learn is that how to take that and let's abstract it a little bit by turning these functions into data structures. And so what happens here is you see these little bracket cont1, cont2. That's the actual functions that have been moved someplace else, and I didn't include them here, but this is just the infrastructure for everything that goes around these little continuations that are defined somewhere else. But they're simple little functions. And so that's all you do here, is you turn those functions into these little make cont and apply cont continuations. So pretty mechanical, straightforward. Then the next thing you do is you actually, two parts, you, instead of passing arguments to these continuations, you put the values of the arguments in these registers. And so, it's very sort of machine-oriented, sort of using the word register even is, something that's sounds like hardware. And it is. It's something that you can actually implement this in assembly language if you wanted to. So instead of passing in arguments to the continuations, you set registers, and then you just call the continuations, and they get their values. So you set them in the calling program, and then you get them when you are actually using them and getting ready to call your continuation. And then the second part of that is you get rid of the actual function calls, so you don't apply the continuation anymore. You introduce a new register called PC, and then you set what program comes next, the function comes next, and then you have this thing called a trampoline. And you just start it up here, and you start the trampoline up, and it sort of bounces between continuations. And it runs that. And at that point, you can really implement Scheme in a language that doesn't have any kind of fancy, even function calls, really. It can be something like assembly language. And then the very last step is, and it's pretty syntactic, mechanical transformation, is to just take that and turn it into Python. And once you do that, you have a full continuation, call CC, the whole shebang that's implemented in whatever target language you want. So we did that, and probably I asked Jim early this morning, thinking about what kind of questions you might ask Jim so I could ask him so I could answer you. One of the questions I asked him was, what was the hardest part of writing all of this code? And perhaps the step number one was the hardest. Not just writing all of this code, the interpreter in continuation passing style, but also, when you get to the end and you write some code and you run it, you might want like error messages, undefined variable in line 3, and that got really complicated in order to pass all that source code information along. Even like you have macros and things like that, you've got to carry all of that information. So Jim pretty much wrote all 6,000 lines of the continuation passing. It doesn't sound like too much code, actually. And this has got comments. It's not really lines of code. It's just that's how many lines were in the program. And that gets transformed into the data structures version, which has about 9,000, and then transformed into a register machine. It's a little bit more verbose. And then, strangely, the number of lines actually diminished in the conversion to Python. I'm not really sure why there are fewer lines. Maybe, I don't know. But what's interesting about this, we end up with 4 versions of the scheme that all work. You can run each one of those independently, and you can, in fact, test it on Scheme code across the board. And that's really useful for debugging. First you want to make sure that your program specification for your language, the continuation passing style program, works. and you catch bugs there. And then you apply the transformation and you run the same test program, apply the transformation, run it again. And then finally in Python you can try it and see, make sure it works. So I'm not going to talk too much, but there is a macro system in Calysto Scheme. It's not as powerful if you know Scheme scheme or racket schemes, either define syntax or syntax rules. This was a custom implementation that we wanted to make it so that users, students, and others could do macros, but neither Jim nor I understood the full complexity of the ... ellipses, which is really an expressive way of creating macros. But we didn't know how to do that. So we made a simpler system. And you can do some pretty complicated things, but not as easily as you can in some of the other macro systems. Sometimes you might have to write helpers. And it's definitely true that our macro system is not hygienic. So we made sure that all the macros that we use in the language were, but a user can create things that are not. So you heard this morning a lot of really interesting things about non-deterministic systems. And in the paper, if you want to go see, we actually built this into our version of Scheme, like you saw this morning. This is a slightly different use for non-deterministic systems. This is, you choose a color, you apply some constraints, and then you just list out the answer. So it's a really powerful programming style. And I'm not going to talk too much about that. That example has a couple of, one macro and another just wrapper around choosing a color. But you can try that out on a different map. And you can see, yep, you really can color a map in 4 colors. But what's perhaps more interesting, or not interesting, but probably useful, is this is a TensorFlow model written, basically this is just like Python code converted to Scheme. And so you have these, this let star and a bunch of things defined, and then you create a model and you train it. Pretty simple. But what's really cool is because it's written, instead of just setting the optimizer to something, you use this choose operator, this non-deterministic operation, just says pick one. And so it picks one and you train the model. But sometime later in the future, you can say, let's run that again with different. This is sometimes called hyperparameter search or a sweep in machine learning. You want to run the same model with a bunch of different hyperparameters. So you just say choose, and nothing you need to do special. It will just go back and choose different values for those hyperparameters, run the model again, and you end up with more results. So really, beautiful, elegant way of doing what people do today in a really practical way, but taking advantage of that non-deterministic system. So this is something that, well, should be near and dear to the speakers that talked earlier today. They spent a lot of time talking about, how you analyze, a non-deterministic FSA. Well, we didn't really think about that. We thought about, we were going from Python into Scheme and making just a generically useful system. So we have a stack trace. Now this isn't, this is Scheme, so there's not really a stack. But we pretend like, yeah, it can definitely grow and grow. And in fact, you wouldn't want to turn this on when you have an infinite, recursive function. But for students and perhaps other people that are, trying to debug their Scheme program that doesn't necessarily use, the non-deterministic aspects, you can just have a stack trace. And so for people, switching between Python and Scheme, this looks familiar. In fact, some people would look at that and say, oh, you implemented this in Python. Yeah, but that's not from Python. That's, we had to build that. This is written in the continuation passing style interpreter. So we had to do all that formatting so that it would get translated and eventually come out in Python. So one thing that's really cool when we got done, when we made the system so that if there are Python functions available, you can call them from Scheme. And I can talk a little bit later if there's time about the environment, the way this works. We still have the full contours of Scheme, but then there's a top-level environment of Scheme and then a fallback environment that's Python. And so if you don't find the variable that you're looking for, you will pop out on that very last layer, and if it's in Python, oh, I'll use that. So import NumPy, all it really does is put NumPy in the Python environment, just like in Python. But then you can call it from Scheme, and if you notice, here I'm creating a matrix 3D out of a bunch of nested lists. And lists, these are linked lists, and it works. And the same way, here's an example using matplotlib. If you're a data scientist, this is one of your daily tools that you would use. So importing this Python library, you call it and then you show it. And this pops up a window that we didn't have to do anything. This just worked right out of the box. Here is one where we had to do a little bit of work, and I'll talk about this later perhaps. This is a macro or a magic is what they call them in Jupyter. So this %plot inline, that says if you do have a plot, then put it inside the notebook. And so instead of popping up a window, it's in this document so you can share it, and that picture of the plot appears right there in the document that you're sharing. So how did that work? Well, it did take we had to do a little bit, but it was in general, not specific to any Python library. What we did was we made the con cell in Scheme, which is just a car and a cooter in a box. It's a linked list structure, but we made the cons class look to Python like it's an actual list. So when you pass in something to matplotlib or NumPy, it looks just like Python thinks it's a list. And so it's just like, oh, I'll take item 1 and 2, and what's the length? So it's not fast to treat a linked list like a list, but it only gets used when you're actually calling something into Python. And so this makes an amazing number of things work when you're calling Python code from Scheme. We do have some support for doing Python-specific things. There's a Python eval, Python exec. In Python, if you don't know, there's actually 2 different ways of evaluating things. You can have expressions and you can have statements. So you have to use different kinds of evaluation on them. We also made a define bang so that if you want to define something in the Python environment, you can do that. And also we have this cute little wrapper that you can take a scheme function of arbitrary complexity and you wrap func around it, and that turns it into a Python function that you can call. And it's just like the sum that we saw. It's the continuation passing style stuff with a little bit of header on that so it can call in and call back and get the result back out. So one of the other things that we did was instead of building all these %, and % commands in Calysto Scheme, we actually worked with other people in the Jupyter environment to make all of these meta commands available to other languages. We thought it would be a waste if we put all these meta commands in just our Scheme version, whereas you have another language, we want to be able to take advantage of these meta commands. So we spun those out into something that we called meta kernel. And this is a really interesting magic. This PX is parallel execution. And this comes from the Jupyter world, the idea of having a cluster and being able to run things in parallel. But very easily, you can run Scheme code in parallel. And it's not as complicated as some parallel programming systems can be, But it's very handy that just in a notebook you can mark these cells. I want this code to go to all of the nodes, and this one I want to just run locally. So it's, you can do some of that kind of thing in, say, Racket, but it can get pretty complicated, and there's different kinds of limitations. And this way, it's pretty straightforward. Simple, it's just like ship code out, run it in this environment, get the answer back, and then you can do something with it. So I taught programming languages course at Bryn Mawr College for many years. And back in the day, that there was the version that I had at Indiana, we had to implement Scheme in Scheme. And as a student, I will admit, I was a little bit confused for the first couple of weeks. I'm writing a language that I don't really know, and I'm creating an interpreter for a language that I don't really know. And you can kind of get mixed up in the layers. When I taught this myself, I thought, you know what, I'm going to do this slightly differently. Especially because at this point, Python is getting more and more popular, so students are picking up Python in other classes, other places. So I had them implement Scheme in Python. So Python's a language I know a little bit, and so Scheme is the odd duck out, and has these weird semantics that don't exist in Python, and so this is a really nice way to teach that. And you can do it fairly straightforwardly in Python. And so what's interesting though is that now we have a scheme. We can actually do, so the first part of the semester we implemented Scheme in Python. Now they know Scheme a little bit. So now let's actually switch languages. And what you can do pretty easily with Calysto Scheme is that you can write Scheme code that interprets Python. Now this is crazy because Python syntax is, that would take you years probably to implement a Python parser. I don't know, maybe you guys can do it better with your non-deterministic systems. But we cheated a little bit. And so you see the very top line is import AST. So because we can take advantage of Python libraries. Python has a library called the AST, Abstract Syntax Tree, and you can see it used here at the bottom, ast.parse. So that takes care of a lot of complexity, and it gives you back an abstract syntax tree that you can then write your interpreter in Scheme using the Python AST. And so with just a little bit of code, you can start out and you can build a real Python interpreter in Scheme. All right, so I think that I will probably leave this here. Yeah, I will open this up for questions, and thanks.
Hi. To do the conversion between the Scheme interpreter and the CPS version and the other ones, did you use automatic like tools to do it, or
Yes.
did you do it by hand? Oh,
No. So this is a development system. So you can actually use this in general. You can take anything that's written in continuation passing style and apply these transformers to it. And you'll get out, you take the CPS version, apply the transformer to it, you'll get a data structure version, apply that to another transformer to it, and you get the register machine, and then you apply another transformation to get the target language out. And this is all on our GitHub, Calysto Scheme. If anybody's interested, it would be really interesting if somebody wanted to explore, a visualizer for non-deterministic FSAs or even deterministic ones. I know it would be really cool that, instead of having a backtrace here, to pop up a little diagram and say, you've got an error right here, and be able to explore that and say, where did that error come from? How did I end up here? What's the problem? Did that answer your question? Yeah. Okay.
Great talk, thank you. So I have I guess, two questions in one. First one is why Python, and the second one is can you apply this to other languages as well?
So why Python? I guess Python, because it's really such a rich set of batteries. You know, being able to do it on machine learning, being able, you know, just the vast set of libraries that exist with Python, I think make it really interesting as a pathway from here to whatever you might be interested in. Yeah, I think that's, originally it was in C#, which, did I mention we had funding from Microsoft? So I think I'm in the right town here to say that. So, you know, having the implementation in C# made a lot of sense. Everything was open source. But yeah, I didn't really mention the speed of Calysto Scheme. And you can imagine it does not run very fast. But I'm glad we did it in Python. You know, it's not really functional to do the kinds of big computations that you do in Racket or in Shea Scheme. But for this kind of environment, for exploring, testing things out, it's really quite useful. In same ways that, you know, Python is useful. Python's pretty slow. And then this system is built on that, which is even slower than that. And you had a second part?
Well, it was, have you tried it in other languages, but I guess C#.
My dream is to do it in JavaScript. I think that would, you know, it has a built-in just-in-time compiler. I think that would scream and would be a lot of fun to try that.
Yeah, it makes sense. Thank you.
Yeah.
Okay, this is sort of more of a general question. You mentioned that the students back then, the first robot they got was only in Python, and there was a lot of research still to be done for programming languages related to AI. Now, what about today? Is there still, how important is programming language research for AI? Is it even important at all?
I think so. I think there are so many unanswered questions. The original version that we had, that it was basically a hypothesis. Can you write a bunch of libraries, robots and music and art, and then have the students move between different languages using the same libraries, so keeping those fixed, but seeing how to do the same thing from different languages? That didn't go anywhere. We didn't get funding for it, so that was a bad idea. But I think there's lots of ideas in programming languages yet to be explored that we're really just now touching the tip of the iceberg. Yes, I'll be around, so all night. If you want to do dinner or something, we can talk some more.